This is my presentation for Lab 4 on oscillations. We are being asked to analyze the movement of a weight on the end of a spring and create a model based on spring gravity force to predict this motion and then compare. We have chosen this model because it takes into account the most powerful forces involved and should give us an accurate result. We are interested in the results because it will show us if two fundamental physics principles are accurate at predicting real motion. Our system is the weight and the spring. First, I will discuss the physics principles we'll be using, and then I will describe the initial conditions and the representations of those physics principles in Python. Finally, we will compare our observed and predicted data and discuss some what-if questions. So there are two physics principles that are in play today. The first being Newton's second law, which states the acceleration equals force divided by mass, and since we are not given acceleration, we'll use the forces in the position update formula instead. The energy principle states that energy cannot be destroyed, but it may be transformed. This means that in our model, net energy should be constant and delta E should be 0 because no energy should be entering or leaving the system. And here's an illustration I made to show the energy principle. You can see that the energy is moving between the two objects in the system, but it is not leaving because it is a closed system, and because of this, delta E is 0. And here are my initial conditions, including the mass, the position, the velocity, the time, and delta T, and of course gravity. Here are our spring physics. First, we must calculate the K constant with the equation we've been given, and we know the mass, so all we need to find is the y period, t, by finding the distance between the peaks of our time versus y graph. And we found that the average period is about 1.52 seconds, so our K constant is about 6.9. And now we must find the initial length with the formula we've been given here to the right, and we can now plug in the information we know to find that the initial length is about 0.126 meters. And so here you can see where I input the spring constant, the initial length, into Python, and also how I find the length at any given time, and the position vector, and that s, the change in length, is length minus the initial length. And so here's how I calculated the system energies. The only energies acting on our system are kinetic, potential gravity, and potential spring. And we already know the equations to find these, so we just need to convert them to Python, and you can see how I did that once again on the right. And here's Newton's second law. In order to update the position of the ball in our model, we need to use Newton's second law. And the only forces acting in our system are the force of gravity and spring force, and so they together equal F net. And we'll use F net divided by mass to be our acceleration in the position and velocity update formulas. And you can see how I did that, how I found the force of gravity, the spring force, and then F net is those added together, and then how I updated the velocity and the position. And so you can see on my model that delta E is 0, which is correct according to the energy principle because there is no net change in the energy of the system, it is only transformed. And you can also see that the magnitudes of the change in potential spring force and potential gravity are equal and opposite, and that delta K is decreasing over time, and this is likely due to energy. So to compare the observed and predicted positions, I would say that the model very accurately predicted position in both the x and y directions. There's an obvious delay between the model and the experiment though, and this is probably due to some error in my data gathering analysis. The magnitude of the model is also slightly smaller than for the experiment, the model being the blue line and the experiment being the red line. And this is probably due to inaccuracies in calculating the K constant and the initial length. The differences are also due to the fact that in real life there are more than just two forces at play, such as air resistance in the opposite direction of motion and airflow in the room that could be in any direction. And so our first what-if question for your model system is the energy principle satisfied. The energy principle states that energy cannot be created or destroyed, only transformed. This means that within our closed system, delta E should be 0 because no energy leaves the system and no energy is created. My model satisfies this principle because in my energy chart, delta E, the orange line, is always 0. And our other what-if question, we are asked to make two estimates of the oscillation periods from the x position data and the y position data, and then compare and discuss. The oscillation period is the distance in time between two equivalent points on two waves, and I have chosen to use the very top of the peak for this. You can see I found the distance in time between each peak, and this meant that for the x direction, the average oscillation period was about 1.63 seconds, while for the y direction it was about 1.5 seconds. You can see on my graphs the oscillation period for the x direction is slightly larger than for the y direction, and since the only forces we are taking into account are spring and gravity, and both work primarily in the y direction, it makes sense that the oscillations in the x direction would be slower because there is less work being done on them. So, in conclusion, in this lab we observed the motion of a spring and created a model to predict the motion. We found that both the energy principle and Newton's second law still hold. Our model is very close to reality, and the differences are probably due to the assumptions and simplifications we made when calculating the initial length, the K constant, and the forces acting on the spring. In the future, in order to make the model more accurate, more forces should be taken into account, and more time should be spent observing the path of the actual spring and calculating K. Thank you.